Good afternoon, everyone, and welcome to today's webinar, Virtual Reality, a Training Tool for Biological Sampling. I want to make everyone aware that we may experience some technical difficulties due to so many people being on the network. In addition, this webinar is recorded. For webinar support, please send an email to caesarcoms@epa.gov. Next slide, please. Your audio is muted. So to ask a question, select Q&A on the right side of the screen and type your question in the Q&A box, then select send. Feel free to type your question in the Q&A box at any point during the webinar. We will also have a Q&A session at the end of the webinar. Closed captioning is available. Select captions/subtitles in your video controls. To change the caption language, select Settings, then Captions/Subtitles, and choose a language. Next slide, please. Anyone on today's webinar may receive a certificate of attendance. You will need to attend this live webinar for 60 minutes. If you do not request a certificate of attendance upon registration and would like one, send an email to caesarcoms@epa.gov. Just a note, EPA cannot guarantee acceptance of certificates by your organization, nor can certificates be provided for viewing the webinar recording. Next slide, please. Thank you for being with us today, and now it's my pleasure to introduce our speaker, Timothy Bowe, a geographer in the Office of Research and Development's Center for Environmental Solutions and Emergency Response. Timothy?
All right, thank you, Amelia. Just checking and making sure folks can hear me.
Yes, thank you.
All right, good deal. Well, let's get started. So before we get going, though, I do want to recognize my co-authors in this project, Dr. Berth Calfee from US EPA and Leroy Mickelson. I also want to acknowledge Dr. Ellen Shoemaker and Lucas Blair from RTI. These folks were essential in getting this project off the ground. So today we're going to talk about a pretty interesting technology that I'm sure some of you who are attending have either owned or have played around with. For those of you who have not, we'll go over some of the background of what virtual reality is and specifically what EPA is interested in using this powerful tool for. So just a little bit of a background for what we're going to talk about today. It's EPA's mission to protect human health and the environment. But it's also EPA's Homeland Security Research Program. It's our mission to provide science and technology solutions to effectively respond and recover from disasters. This could be a whole gamut of different things, such as technologies that support the characterization, the decontamination, i.e. the cleanup, and the management of waste that is generated by that. So we not only focus in natural disasters, we look at human-caused disasters as well, such as chemical, biological, and radiological cleanup. Again, a number of different technologies are used in the response, both from an operational perspective and also technologies to assist in that cleanup. Some of those technologies are used for training as well and situational awareness, which virtual reality is exactly that. And that's what we're going to talk about today. We're going to cover some of the objectives that led to EPA in terms of investigating this technology. And we're going to talk about the technologies that are used to make this virtual reality environment a real thing, but also talk about the training platform and next steps in terms of what we're going to do now that we found this effort successful. And we're also going to do a little bit of a pop quiz. Now, don't worry, this isn't going to count against your certificate of participation. I do like having involvement from the audience, so we're going to use an application called Slido. Slido is actually a web-based app that allows the audience to partake in a few different trivia questions that we're going to present throughout this presentation. To partake, all you have to do is scan the QR code using your phone. If you have an iOS device, you can turn on your camera and scan the code and then click on the browser link that pops down. If you don't have a phone available to you, you can also join in at slido.com. The event number is 39264. That again is slido.com, event code number 39264. So let's talk a little bit about what virtual reality is. Again, some of you may have already played with virtual reality or partaken in virtual reality and playing games, but It's essentially a head-mounted device that fits in front of your eyes that allows you, the user, to see as if you were actually in that environment yourself. So a lot of people say it's really analogous to real life. And as the technology has evolved over the years, the developers of VR, and there are a number of them, have really gotten this technology to the point that it's almost lifelike. Now, it's not just visuals, it's also the movement. So your head, your hands, your feet, and your whole body is tracked. So as you move, this movement is duplicated in the VR simulation as well. When you take other sensory such as sound and include that with games or maybe even action movies into some contexts, this really changes the way we absorb media. It allows us to actually play in real world scenarios through a headset, and really changes how we humans interact both with each other, but also with these dynamic environments that we present. The popularity of VR has increased extensively in the past few years. I'm sure you have either seen it advertised on TV or read an article about it online, but the development has, and the hardware development has gotten to the point where the costs in terms of implementing VR have decreased dramatically. And in fact, I would guess somewhere between 50 to 75% of homes that partake in video games have a VR headset at their disposal. So VR is great when it comes down to video games or consuming digital content, but you might ask, why are we interested in terms of research? We do know from historical research that VR allows you to augment realism, and that realism can also be learned. So in other words, if I'm doing an action in real life, I can also emulate that action in a virtual sense. The learning that is obtained from that virtual event is also similar in terms of memorizing or remembering how that action took place. So in other words, as you learn tasks in VR, we actually see very similar outcomes in terms of people learning how to do real life applications. Now, what's interesting about VR is that since you are wearing a head device, we can control what you see. So therefore, it's a lot easier to frame someone's vision, i.e. there are no distractions, there are no cell phones or no computers. You are focusing in on that application, whether it be a game or in our instance, training. This allows folks to really work at their own pace, which again has also we've seen evidence in research that you tend to learn better when learning at your own pace. EPA is interested in this technology for a number of reasons, and we do a lot of training with our first responders to both respond to incidents, but also down into the detailed processes in which we must take, again, to characterize and respond to an event. It's a great training tool, and it's something that we've really just touched the surface on. This project is going to talk about a biological surface sampling simulation that we've developed, and how that sampling or simulation is being used to train people and where we expect to go in the future. So the next slide I'm going to show here is going to show two videos, and I want to talk about the objectives that actually led us to this research effort. The first is that training in person may not always be ideal, and COVID is a great example of this. We have all turned to our computers, our televisions, etc., for various different learning experiences where in a normal situation we'd be able to be in person. But also the exercises that we partake in tend to be very expensive, and the events that we have to mimic are sometimes once in a lifetime situations. So it's very costly and time consuming for us to simulate these environments. When we are able to conduct field scale exercises, we like to simulate a gamut of different things. Sampling is one of those things. From our previous experience, our samplers have performed quite well, but there are also learning opportunities that come out of this. I want to draw your attention to, again, the two videos at the bottom here. On the left side, we have a person collecting a biological surface sample. That person is actually performing the sampling procedure correctly, but that person is kneeling on the ground. If you think about the type of events that we respond to, these can be contamination incidents. If that person is kneeling on the surface, that contamination that was on that surface is now on that person. You also risk tearing the material as you stand up, which can expose the sampler to potentially hazardous substance. On the right, we show two samplers who have just finished taking a biological sample and are actually working on putting the sample in a vial so that it can be shipped off to the lab. Those of you who are experienced in sampling probably see some issues here, but I'll go ahead and point them out. When you take the samples, it's essential that the sample actually doesn't touch any other surface besides the surface that you wanted to take the sample from. We refer to this as an aseptic technique. In other words, I don't need to be introducing anything else outside of what that thing was that I'm sampling for. So when you touch the head of the sample device, you're potentially introducing contamination to an otherwise clean sample. Those of you who are not experienced in these type of events, it's important to realize that this sampling will determine how we as EPA, our partners, focus or plan out decon. So in other words, based on what we find will determine our strategy and the applications that we use to remediate an area. But also it's involved in terms of clearance too. So if I've conducted my decontamination, i.e. in this situation, we were simulating Bacillus anthracis, which is the causative agent behind anthrax, it's very important that we know that we've done a good job in terms of conducting cleanup, i.e. each sample that we take is very important in terms of it's either yes or no, is something there, so I can determine if additional cleanup needs to occur or if I can release people back into the environment. Hello, just doing a quick mic check. Seem to be having some internet difficulties on my end.
We hear you, Tim.
Okay, good to resume. All right.
Yep, you can go ahead.
Perfect. All right, well, we're back. So yeah, again, 2020, all kinds of interesting surprises. Folks in RTP are currently experiencing impacts from a hurricane, so we're having power outages and all kinds of interesting things. So we'll go ahead and pick up where we left off. I will resume back on objective number 1, and that was developing a training platform to enable folks to train for biological sampling techniques using virtual reality. So we'll go ahead and move on to the next slide. All right, so objective 2, if you can imagine a biological incident, especially if you're a responder, and having to enter an area that you are not familiar with, there are a number of challenges one might face. Not to mention hazards, but also if you're trying to design a sampling plan, these plans can be rather involved. There are a number of different approaches that we typically use, but we tend to focus in on judgmental sampling, which is essentially us based on lines of evidence determining where to sample, but also statistical sampling. Statistical sampling essentially provides a sampling plan based on some statistical approach, i.e. we have some given probability that I'm 99% confident that I'm going to find everything and it's safe to allow folks to re-enter. Now, this plan that we have shown on the screen here at the bottom was actually from a subway platform. That subway platform alone had roughly between 150 to 200 samples. You can imagine that as a team entering this is not very helpful in terms of where do I go. It's actually overwhelming. What we hope to use virtual reality for in the future is that we can take these two-dimensional maps and turn them three-dimensional. So if I could send in my teams in a virtual way, i.e. they walk through the environment, they can see their samples and where they're going to be when they actually walk into that environment, they can actually conduct the sampling in a more efficient way. There are no surprises when they walk through the door. They can immediately get to work and start taking their samples. Now, another interesting thing here is that this 2D map is absent of any landmarks. DoD has tested this approach with paratroopers in terms of dropping them into areas with virtual reality and having them learn which landmarks they need to use to gauge the direction that they need to go with or go in to proceed with their mission. This is a similar approach where if I can show my sampling teams where might they sample in retrospect or perspective of the landmarks that are in, for this example, the subway, it allows folks to actually find these very discrete samples a lot easier otherwise if they were looking at a paper map. So let's do a pop quiz question, and we have a few of these as part of today's presentation. So let me pull that up here. I'll go ahead and read it while I pull it up. What 1993 video game did the Department of Defense repurpose to train Marines? A, Mortal Kombat 2, B, Myst, C, Doom, D, or Star Fox? And again, you can scan the QR code shown at the bottom there to join in on the Slido event. And once you do that, you should be prompted by a page that allows you to enter your name and information. You are welcome to use your real name. You can also use an anonymous name, but once you hit that go button, you should then see a quiz question. So we'll go ahead and start the quiz. So again, scan that QR code, take your best guess as what you think the answer is. And once everyone has voted, I will display the results on the screen. Now, in keeping with faith of video games, you are always going to have winners and you're going to have losers. So we're going to post the leaderboard once everyone's had a chance to vote and we have concluded our few quiz questions. And again, they will pop up throughout this presentation to kind of keep folks on their feet. So we have quite a few responses coming in. We're up to 30 responses. Let me go ahead and show folks what it looks like thus far. So let's open this up. I have to cooperate with my my internet here. Let's see here. Let's see the results. So it looks like Doom is the overall winner. Mortal Kombat's a really good guess. I think hand-to-hand combat is important. But the correct answer here is actually Doom. DoD worked with the Doom game to actually develop something they called Marine Doom. Marine Doom came out in 1996, was used to train Marines in both how one might approach a battlefield, but also the teamwork that it would be required to work together. So they would get instructions, they would be given maps. And for those of you who have ever played Doom, and I think it's almost 26, 27 years old now, that might make you feel a little old. The graphics weren't that great, but you got the picture in terms of you could still work together as a team. You would use your resources to understand how to navigate areas that, again, were kind of foreign to you. And this was really one of the key examples that we wanted to emphasize as part of this project, and that we should really emphasize as part of any EPA project. We're kind of jokingly assuming that, video games are very analogous to some of our research, but in reality they are. But it's also the technology that they're based on. It's a lot cheaper for me to repurpose a pre-existing game platform that the gaming industry has invested potentially billions versus me coming in and reinventing the wheel. So that's what we really focused in on this project, and we'll show an example of it here, how we've modified a pre-existing game technology and created a simulation to both save us time and money, so we can repurpose that money and put it back into the simulation itself. All right, so in addition to collaborating with the game industry, it's also important to point out the collaborators that actually helped us make this project come to fruition. Within the Office of Research and Development, we emphasize that it's important to work with the EPA regions, but also other federal agencies, states, and local. There are two collaborators that were extremely important in the development of this project, and I want to give them kudos here. That was the Raleigh Fire Department, specifically Captain Trey Tart, in the North Carolina Emergency Management Department, specifically Justin Graney. He was also with the department, North Carolina Department of Safety. They came to every meeting that we had and also brought with them emergency responders who could potentially be using these applications. In addition to these one-on-one meetings, learning about the problems in terms of the things that they face when training people and how our technology could be repurposed to help them, they also allowed us to use the training space. So this is key, and we'll get back to this later on in the presentation. But for this event, we had a real-world environment that was exactly mirrored in the virtual reality environment, but also the real environment as well. There are some interesting scientific studies that can be conducted when assessing the learning efficiencies when you have two things, one in real life and one virtual, that you can compare against. Also, if you remember that the key here is to not only develop a training tool to conduct sampling, but also developing a system that enables samplers to find the correct locations that they're supposed to sample. So we could simulate that in the game as well in real life, which should produce some interesting research that we hope to resume once the COVID situation improves. So I've talked a lot about simulating the environments, and in video games, that's typically done through a lot of artwork, right? Because the things that we see in most situations don't really exist. But in our situation, it does really exist. To do that, we had two different options. One, we could have paid someone to develop these very specific 3D maps. However, this process is very costly, as it takes someone time to sit down and draw all of these different environments, the different things that reside in these environments, and the actual textures that go in these environments. What we used as part of this project to expedite this is a technology called photogrammetry. Photogrammetry is very similar to actually the process of taking pictures. And as you think about a ball in a room and you take pictures in a 360-degree rotation, we have the capability to generate a 3D space, given that the computer is able to track where in that location that picture was taken from. The result is a 3D image that also has imagery or textures, in this case, in the background of it. It's actually a very cost-efficient way in developing 3D images, and it is a technology that is starting to be used increasingly in things like GIS, but also in video games when trying to draw out these complicated environments. So we decided to apply this technology to our training scenario, the Keeter Training Center. It took us about 2 days, and about 1,500 images were collected. We actually brought in professional photographers to take these images. And one might say, well, that's a lot of time. And that's true, that is a lot of time. But we are still trying to perfect this approach. So we only had one opportunity to do this. As this training location is used quite often for training firefighters, we wanted to make sure that we got enough imagery so there would be no problems in terms of developing the environment. There are solutions to make this process more efficient, and we are looking into those as future projects within within the Homeland Security Research Program. So we go in, we take pictures, we load these pictures into a computer program. That computer program, as you can see on the right, takes these images, blends them together, and creates a 3D image. From that 3D image, we basically smooth out some of the artifacts that were generated by the image. And at the very end, you have a smooth 3D image of a room using pictures, i.e., again, textures that simulate that of the real world. This required a lot less time than it would have for someone to recreate each room in this facility. But it's also lower cost and lower turnaround time. It saves the tax people money, but it also allows us to focus our funding into areas that are more pertinent in terms of developing the simulation. Now, let's talk a little bit more about the training platform. As I've mentioned earlier, the VR system consists of a headset. If you look at the picture on the right, you can see the gentleman wearing a headset. So all he sees is some kind of visual. That visual is being projected onto two separate lenses. Think of them as mini TV screens that have super high refresh rates so that when I'm seeing it, my brain is thinking that it's real. But also we have hands, or what we call wands, that the person uses to simulate their hand movements, but also grabbing things in the environment. Some of the latest versions of this technology, you don't even have to have the wands. You have a sensor that is embedded into the platform that uses a camera to track the hand movements. So in other words, I can move my fingers within within real life, and you see that in the simulation. This is very important when you want to pick up something like a pen in virtual reality, because you can actually use your fingers, your arm movements to actually pick up something in a virtual way. Again, this is really important for us because we're training on something that requires a lot of dexterity. We also have a computer. So this VR headset has to connect to something. The computer basically takes the design that we have and creates a 3D environment that is reactive to how the player is working or behaving in that virtual reality environment. These visuals are created by software in that we refer to as a 3D engine. All games and some movies that you've seen use 3D engines, and these things can be very complex. And that was the benefit, again, of repurposing, especially in this purpose, a pre-existing technology. The engine that we used is called Unity. Unity has a number of games that have been developed and has seen a lot of success. So it was very cost efficient for us to take that pre-existing game platform and modify it to include our visuals, but also the processes of taking samples. So let's take another look at our trivia here. So I'll pull back up the quiz, and let's start our next question. And I'll go over that question. And again, if you closed out on your browser, you can quickly rejoin by scanning that QR code. So the first question, or the second question rather, that we're going to ask folks today is, how much money do you think was spent on video games from January to June of 2020? Now, keep in mind that a lot of folks had a lot of time on their hands, right? So the time spent maybe driving could have been spent playing video games. The time spent with family, I've seen instances where entire families sit down together ever since COVID and play a game together. So a lot of money has been spent on this. So take your best guess, and we'll see who wins here. We've had about 18 people vote thus far. Let's wait till that gets up to 20, 22. There we go. All right, let's see the results here. It looks like overwhelmingly folks think roughly about $1 billion was spent on video games in the course of 6 months. If you said 1 billion, you are correct. In actuality, if you include the hardware, it was somewhere around $6 billion. The reason that I'm asking this question, and we're touching on this again, is that the amount of money that is poured into these games is also put back into research and development. We don't have to really touch on the 3D engine portion. There's a lot of money being thrown around in the IT world and development of these engines. So we take advantage of that when we use commercial off-the-shelf equipment. So let's do one more question here. So Oculus, which is a VR brand that we were actually using in the development of this application, is owned by what technology company? A, Microsoft, B, Samsung, C, Facebook, or D, Dell? I'll give folks a little bit of time to respond to this. And one of the interesting things, and isn't necessarily related to this presentation, is that some of these companies, such as the one who we're going to highlight who has developed this technology, are making it specific that you have to have a certain account to partake, which from a research perspective is becoming very challenging. And you'll see why in just a few seconds. So I'll show the results here on the screen. This one's obviously folks are struggling with this one a little bit more. The answer isn't that obvious, but if you selected Facebook, you are correct. The interesting thing here is that Oculus started out as a Kickstarter company, funded company at about $250 million, and was sold to Facebook. And I think 2 years later, so 2014, maybe 2015, for 2.3 billion. So quite the investment. Of course, the technology world is in an uproar because now Facebook is thinking about requiring folks to have a Facebook account to use their technology, which can be challenging if you're developing an industry, a video game or simulation to use that technology. So let's resume with our presentation. So, oh, and I will show the leaderboard when we get to the questions. So we'll see. We'll see who actually won in terms of the pop quiz or the trivia. So the training platform. So we've got our visuals figured out. We figured out how we're going to map a given area, and we've also identified technology that we're going to use. In our case, it was Oculus. So we set forward to develop a training and situational platform using a virtual reality technology that is based on commercial off-the-shelf software. Again, emphasizing the need to save money, but we could use cutting-edge graphics and technology to make these visuals for folks that are partaking in this simulation look lifelike. So in terms of situational awareness, so this is sort of the end result of that. As we were taking photographs of this training facility, it was really exciting because given that it's a training facility, there was some debris. Instead of removing that debris, we decided to keep it in place. This is image you see on the left was actually from inside the simulation itself. So this is not some person standing there taking a photograph. If you were walking around in the simulation, this is what you would see. From a situational awareness perspective, and this may and will go beyond EPA's purposes, that if you're actively collecting evidence, you can see the amount of detail that's provided in this photograph. Think of this powder as something maybe more nefarious that one may want to investigate. You can get a good idea of the location, but also the detail in terms of how it's spread out. From a planning perspective, if you were planning out your sampling approach and you were trying to figure out where one might place samples, this type of approach might give you a good idea of where you want to take samples. So although we've talked about the effort of us having to go in and take photographs, we hope to use this technology in the future by way of either backpacks or automated technology such as unmanned vehicles to actually enter these environments, take imagery, and then quickly build out these 3D environments. So again, if I were an emergency responder or I was leading an emergency response, I would be able to send in these capabilities and then virtually walk through the environment to understand the hazards that are present, but also evaluate how I'm going to approach the problem and plan out my process of attack. So the training platform consists of two separate views. You have the trainee view, which is the person wearing the VR, and you have the trainer view, which is the person or the instructor who's leading this training effort. They each have two different views that are available to them. The trainee obviously sees the virtual environment, but they have a number of different options. And this is important because the virtual training environment allows us to not only evaluate, but dynamically change what happens based on the level of difficulty that is selected. So in this training platform, the user or the trainer can select the level of difficulty. This level of difficulty will change in terms of if I walk into an environment and I have selected a hard level of difficulty, I will not know where my samples are, i.e. I will not see them. I would have been given some information of you need to sample at this location, and then another location. I would have been shown a map, but I'm walking into this not knowing exactly where those are. This helps folks prepare. Again, when you enter these environments, you're under a lot of stress. It's easy to forget, but when you train in environments such as this, it's much easier to relax, recall what you were supposed to do, and go take the samples in which the locations you were supposed to take them in. Within the VR platform, we have 3 different sample types, which are commonly used to sample for Bacillus anthracis. That's microvac, swab, and sponge. And you can see the virtual recreations of those on the right side of the screen here. The samplers then utilize the EPA CDC validated procedure. And again, there's quite a few processes involved in this to ensure that you're collecting or accurately collecting a sample from that surface that the user must complete in this virtual environment. And I'll show a video of this here shortly that shows how much interaction that is with the user as they are applying that sample to the surface and performing the various different sampling procedures. The trainer has a view that he or she can see the simulation, but also see the metrics that are being generated. So on this slide, on the right side, you see an image. This is what the trainer is seeing. So they can zoom in and see, again, the simulation that the trainee is using, but they can also look at scenario stats, i.e., has the sampler navigated to the correct location? Did they select the appropriate tool based on the location or surface that they're sampling? Did they remember to swap their gloves? But it also, and this is where virtual reality comes into play, is that we can assess how well they are actually sampling that surface. I mentioned earlier that there are a number of overlapping procedures that are involved in a biological sample. And those, depending on the sample type, can include horizontal, vertical, diagonal, and perimeter sampling methods or directions. As the user walks up to the surface, they will begin taking the sample based on the method that's been prescribed. The system will, in real time, track the surface area, but also whether or not the sampler is going in the right direction per the sampling protocol. As the sampler takes or conducts the procedure, these boxes that are currently white will fill in based on the surface area that the sampler captured. This information is also collected on the dashboard, and the trainer can see it and determine whether or not, yes, they adhered to the sampling procedure correctly, or maybe you need to work on the vertical sampling direction a little bit more. You didn't fill in the box all the way. So that allows them to evaluate in real time, but we actually have a way to collect the metrics behind this, which is quite interesting. You couldn't necessarily do this in a real world in-person training application. So I'm going to show a video here of an early version of the sampling tool or sampling simulator. And I acknowledge that it might be choppy, but this basically shows the user walking up to a surface and taking a sample. Now, as they start to sample, the green background, which again, you don't see in the latest version, but the background is actually collecting the movement and direction and the speed in which that surface is being sampled. Now, as the sampler steps through the various different procedures, he or she is also feeling feedback. So as they touch the surface, the hand or wand that they are using actually vibrates. So it's a way for us to provide feedback or touch that lets the user know that I'm actually touching a surface and I'm adhering to that surface throughout this procedure. You can see that for testing purposes, this person is no longer adhering to the procedure, but is demonstrating that what he has sampled in virtual reality or the virtual environment, you can see the percentage of coverage in the boxes that have now been filled in, which mimic what he or she did in that virtual environment. So in conclusion, we've talked about a virtual reality platform that was developed in collaboration with state, local, and federal, including the EPA regions, to create a simulation where folks could train on various different biological sampling procedures. In essence, this was a feasibility to determine whether this could be done, and we overwhelmingly answered that question as a yes. It is possible, and it allows us to collect information that, from a traditional perspective, in a classroom, one may not be able to collect. Also, we wanted to develop something that could potentially be used in the future to create situational awareness. To do that, we use photogrammetry to quickly build out the environments in a 3D way. And this allows us in the future that if a real-world incident were to take place, or if there's a new environment in which we want to train folks in, we could quickly develop 3D environments within this engine and send teams into a virtual environment before sending them into the real environment, which there are a number of advantages to doing this. The platform, again, used commercial off-the-shelf hardware. So the visual or the headset that you see was developed and sold by Oculus. The software was Unity, and we were using the Unity software to develop the system in. This saved us a lot of money in terms of research and development, and we're able to push this money back in to implementing these features within the virtual reality platform. The other outcome of this, which we necessarily didn't set out to do when we first envisioned this project, is that the trainer can review and get a lot of feedback on the trainees' sampling efforts. That feedback can be provided in real time, but I think this hits on something in terms of, and this is where COVID comes into play, where many of us can't necessarily be in a classroom, but as we become more virtually dependent, so we commonly use computers and attend webinars such as this one, that technology is going to become a bigger part of our life. And including the newer generation that's coming up, they see these things as something normal that one might partake in to train in. We have evidence in terms of historical research that shows that this process is likely more effective than in-person training, and that allows people to train at their own pace. So they always say the best is yet to come, and I really think that sums up this project. The beta version of this software was released in July of 2020. We were actually recognized by the North Carolina Emergency Response Committee as an application that would be used by North Carolina in terms of hazmat training. We are working on introducing chemical sampling methods in new environments. You could imagine the type of environments that we might be interested in terms of stadiums, airports. We would like to include those so people can train in these environments as well when they were using the simulator. The upcoming research is something that I'm very excited about. I also have to give kudos to my managers as well in this, in that there is a negative connotation about using virtual reality a lot of the time, and that it's closely associated with games. As you can imagine, a research and development project within the government that's actually looking at a video game is something that could be contentious, but I think folks saw the potential of this technology, and we were able to get this effort funded, and the outcome exceeded our expectations and actually allowed us to work with stakeholders that we've never had the opportunity to work with. In other words, this was low-hanging fruit that the Office of Research and Development took sort of an approach to that would otherwise be taboo. And I think we found something that is a very powerful technology, but we hope to expand that as well. In our responses, we conduct something called just-in-time training, where prior to entering a hazardous environment, you want to train folks on how well they remember what they were supposed to do and where they were supposed to go. I mentioned earlier in this presentation that there is a real-world environment that this project was imaged after. We are actually going to be conducting a study scheduled currently for spring, but again, COVID might change that, where we're going to send in teams to the real-world environment that will be split, basically, where one team will have in-person training and will use a 2D map, and another team will have virtual reality-based training and will see their samples in a 3D fashion. We're going to conduct a study to see if there are any efficiencies in this. We suspect they will have efficiency, or will have efficiencies in this approach, but hopefully more to come on that. We're also looking at ways to automate indoor mapping. I mentioned earlier that we were looking at robotics to potentially conduct and collect and process this imagery for us. We're also looking at 3D engines for other purposes in terms of modeling. When responding to these type of events, it's important that we have a good idea of where things may have ended up. So if you think of something being released, we use dispersion models. We use fate and transport models to understand once precipitation is introduced, where that contamination may go on the ground. 3D engines nowadays, as I mentioned earlier, have a lot of money being poured into their development. So it would be great if we could repurpose this for other applications outside of training, i.e. that what were once academic models, we could take these 3D platforms that again have the physics already baked in and repurpose them for other things such as dispersion modeling. We're also looking at developing a simulation to support CBR response training as a whole. So think of this as the 20,000-foot view. There's a lot of strategy that goes into these responses in terms of how I might approach sampling, how I might approach decon and waste management. But the outcomes are all tied together, where if I take the wrong approach in decon, it's going to vastly impact my waste, the amount of waste that I've generated, and then I could get myself in trouble. We hope to develop simulations that allow folks to actually play through these and enhance their strategies, where it's better to make the mistake similar to the biological sampling simulation I've shown here, versus making those mistakes in real world when there are real world consequences and outcomes to that. Here's our disclaimer, but in all, that concludes my presentation today. I had promised that I would show folks the outcome. So let's take a look at the leaderboard. Looks like Avery, although most folks listed in this got 3 out of 3, but Avery was able to answer all 3 questions in under a minute and 10 seconds. So good game, Avery. Great job. But I would be happy to entertain any questions folks might have. They could also email me at bo.timothy@epa.gov, or my co-author, Dr. Worth Calfee, at calfee.worth@epa.gov. And so, Amelia, I will hand it back over to you to maybe there are some questions in the chat that folks have asked.
Yes, thank you, Timothy. Great presentation. There are a couple of questions in the chat box. I'll start with the oldest one here. A few slides ago, can you point us to the EPA/CDC validated procedure you mentioned?
Yes, we can. There's actually a link that we can provide. I don't know if we can get this person's contact information, but we would be happy to provide a link to that CDC protocol. But if we can get that information, we can follow up with that guidance.
Next question. What kind of time frame are you talking to map a new facility to where it is ready for VR sampling now and expected in the near future?
Right, that's a great question. So I alluded to earlier on in the presentation that it took us about 2 days to actually image that the Keter Training Center. In some responses that might be acceptable, but in most it's not. We hope to get that imagery time, obviously depending on the size of the building, but let's think of an average a building footprint of 1,000 square feet. I hope to be able to image that in about under an hour. Now, there are a number of technical challenges that come with that, though. You have to not only have the thing autonomously drive around and collect the imagery, but you then also have to process the imagery. And when I say process, you have to take these various different images, blend them together, and then generate the 3D environment that has to hook into, in this case, the virtual reality platform. So right now, I would say if I had to put how long it would take, we're probably talking on the time span of a week. But as I mentioned in the future work, all of those projects that I covered are actually ongoing right now. So we have an effort where we are trying to identify solutions, and also through R&D, and how we might expedite the collection of that imagery. So hopefully more to come, but my objective is that if we were to roll up on an incident, to either send in an autonomous robot or a person with a backpack and collect that imagery within a short period of time, because it does not hold up the actual response itself, and that the decision makers can actually use this tool to make a decision in terms of having or being able to walk through it versus guessing what might be the situation on the inside. Great question.
Thank you for your responses. A couple of more questions wrote in. Have you experimented with drones to do 3D mapping?
Yes, that's a good question as well. For those of you who have are experienced in drones or may have read about drones, having something flying in the air is obviously a lot better in some situations, maybe in some contexts with contamination incidents, but you can also use what we call a swarm of drones. So I can send in 20 or 30 different drones into a facility and have them capture imagery in all of these rooms at once and then pull them back out. That would obviously be much quicker than having to send in a single robot or a person. And we always like to emphasize also that you must assume that some of these technologies, you may never recover them. So a $50 drone is obviously a lot cheaper than $1 million robot, but also emphasizing that I don't have to send a person into that hazardous environment. I could potentially send in a robot to do the work. So drones, airborne drones, and including swarms are something that we're looking into to expedite the collection of imagery.
Okay, another question. What about using floor plans for future imagery?
That's a good question as well. You can generate very simple 3D environments based on CAD drawings. The problem that we've encountered in the past is that if you've ever seen a house under construction, which I'm sure everybody has, is that the skeleton version of that house looks a lot different versus the version that has all your stuff in it. And that might change how you navigate, but also how you collect evidence. From a very basic approach, the CAD drawings, I think, can serve a purpose in that if you're just trying to communicate to someone, hey, take a sample in the left corner of that room and also on the floor as you enter this other room. But our environments tend to be a lot more complicated than that. So there might be some evidence or a sample design that you might need to implement that includes something like a desk, a television screen, etc., that those simplified 3D drawings may not communicate as well as you would with these very precise 3D collection mechanisms. But these basic imagery solutions, they can generate designs in probably in a number of minutes versus days or hours when we're using this photogrammetry approach. So I do think it's a potential solution. It just requires the right application.
Perfect. We have about 1 more minute, and if there aren't any more questions, we'll just wait for another question to roll in. And if not, for those who do not get a chance to ask their question, please reference Timothy Bow's email address on the screen there as we wait for a few more seconds.
All right.
Seeing none. Thank you, Timothy, for a great presentation. And again, those who are interested in learning more about VR or have questions for Timothy, please reference his information and his colleague's information, Worf Calfee. Oh, there's one. So right on time. Okay, the last one. As far as outdoor settings go, how can VR recreate, say, an agricultural plot or field? Can this benefit farmers sampling produce?
Yes, one thing I should have mentioned as part of this presentation is that we have focused purely on EPA's mission. In fact, we've focused solely on just one aspect of that mission. There are so many applications, and in fact, this is one of a few projects that I have here at EPA, but it's starting to become one of the most impact. This has application to hospital settings, to military applications, to industrial applications. Teaching someone how to do a great example of that, because it could be a very expensive endeavor to simulate expensive things in real world versus being able to do that in virtual reality. But you can also introduce things such as what we refer to as injects. So something happens in the background and you might try to pull the user's attention away when really you wouldn't want to do that. So you can create interesting simulations. From a farming perspective, I think this could be an interesting tool. I, for one, have never drove a farming tractor. So if I were to be asked to farm a field, it might be useful for me to actually drive this big machinery in a virtual aspect versus getting me behind the wheel and me potentially running into something or not knowing how to drive it. So yes, I think there are a number of applications beyond just what we've addressed here in regards to EPA. And I think really the bounds are limitless. There's a lot of low-hanging fruit here in how we might apply this. And as the technology evolves, you know, our future meetings, in fact, this webinar, we might be able to sit on the beach and have this versus behind a computer screen, which would be exceptionally nice. Especially given that it's raining here. So that's a great question, and I think it's something that we're going to see a lot more of in the future.
Thank you all for attending. That concludes our webinar. For any additional questions, we're going to send them over to Tim, or you yourself can directly send him an email. Thank you, Tim, again for a great presentation, and everybody for attending. Have a great afternoon. Bye-bye.
Thank you.